Hello, everybody. I'll introduce myself again. I am Pranav. I am a fourth-year PhD student in astronomy visiting from Caltech. I work with Professor Kareem El-Badri. My research focuses on the discovery and characterization of black holes and neutron stars and binaries that are orbited by luminous companions. And today I'm going to be talking about black holes that have been discovered from ESA's Gaia mission and why they're a puzzle in terms of how they form and what different observational tests we can perform of theoretical formation models that have been posed for these interesting objects. So I want to begin. Doesn't
Click on your screen.
Okay, yeah. So I want to begin with some context and motivation for why we should care. And so the goal here is to understand this galactic population of stellar mass black holes. And we think that there are around 100 million stellar mass black holes in our galaxy. But we don't really know much about their mass distribution, their velocity distribution, their binary fraction. And the reason is because right now we're seeing a very small biased subset of that population. So if the entire population is kind of like an iceberg, we're only seeing the tip of the iceberg. And most known black holes that we know of are uh, in X-ray binaries, which are these close accreting X-ray bright systems where the black hole is eating matter from a stellar companion. And that is because these systems are observationally easier to detect. So we're biased toward detecting them. And we've discovered over 70 of these systems as X-ray transients. And black holes have been dynamically confirmed to be present in around 20 of these systems. But binary evolution models theoretically predict, as we will see, that these are supposed to be a very rare outcome of binary evolution, and that these systems should be vastly outnumbered by orders of magnitude by their wider counterparts hosting non-interacting, or what I will call dormant black holes. And these are all lurking beneath the water because they're harder to detect. And in fact, the majority of black holes in our Milky Way are expected not to have any kind of stellar companion, but rather to be isolated black holes. And so even though the progenitors of black holes are massive stars, and up to 100% of these stars are born in binaries, many of those massive binaries can eventually become unbound or disrupted or merge, and you end up with a lot of these black holes being isolated. And isolated black holes are notoriously hard to detect. The only way you can really find them is through these extensive microlensing surveys where they pass in front of a star and magnify it. And we've discovered a grand total of 1 isolated black holes to date in our galaxy with this method. Many more may come in the future through missions like Roman, but I won't be talking about isolated black holes today. What my research focuses on is dormant black holes and binaries with luminous companions, like I said. And here, the luminous star can essentially betray the presence of the black hole as it dances around it. It will be influenced by the gravity of its massive unseen companion, and there will be some kind of variability in the light coming from the star. We'll see either photometric variability in its light curve if it's tidally distorted. We might see spectroscopic variability as it moves back and forth along our line of sight, and also astrometric variability because of its motion on the sky. And so far, we have discovered around 5 dormant black holes in binaries. And if you add up all of these numbers, you will find that over 99.9999% of black holes in our Milky Way remain undiscovered. And so there's still work to be done. You may ask, oh, wait, what about the black holes from LIGO? Well, if you're thinking about the merging black holes, well, surely there should be many black hole binaries in our Milky Way, but the merging events that produce gravitational waves are extraordinarily rare. And that's why we don't know of any of those sources in our Milky Way, and we have to go extragalactically to detect merging black holes with light. So how have people tried to find dormant black holes? So the classical method of finding them is through extensive spectroscopic surveys, looking for what are called single-line spectroscopic binaries, where you only see the signature of one star, and you look for the binaries that have large spectroscopic mass functions, implying that they have a black hole companion. But this is a needle in the haystack problem, and these systems are quite rare. And so false positives are abundant, and only recently we've started to discover genuine dormant black holes with this method. And I show a couple of examples here. There was a detached stellar mass black hole found in the globular cluster NGC 3201 a while back. And there's at least one, if not two, stellar mass black holes in that cluster. And also recently, an X-ray quiet black hole was discovered with a young massive stellar companion in a circular orbit in the Large Magellanic Cloud. But if we look at the trend line of non-accreting black hole detections over time, here I'm showing how many candidates were discovered and how many ended up being identified as false positives and being killed. And so the difference between the number of surviving candidates. Yes, you have a question.
Quick question on right. When you say spectroscopic searches,
Yeah.
Right. You're talking about the radial velocity changes, and
Yeah.
like, what is the typical separation between the star and the black hole in such cases?
So this is probing what I would call intermediate separations, let's say. And so if we're looking at X-ray binaries that are very close systems, and let's say they have orbital periods of a day or less, so around that, and then you're looking at the very wide systems that have orbital periods of months to years, then these RV searches would be good in the middle of that range, basically, is what I would expect.
And what kind of wavelengths do you use to detect them?
So these are all optical searches usually, maybe near infrared. That's usually the range in which these surveys are performed. And you would expect variations of tens to hundreds of kilometers per second. So my advisor has been notoriously called the black hole killer. And so he's responsible for some of these candidate deaths. But as you can see, starting in 2021, this trend line of surviving candidates started decreasing. More candidates were being killed than were being discovered, and so it was approaching zero, which is a bad thing for the field. And you see there's a turnaround at around 2023, which is amusing. So what happened in 2023 that led to this? And this was the release of the third data release of the ESA's Gaia mission, which is very important as a treasure trove for discoveries because it gave us precise astrometry for nearly 2 billion stars in our Milky Way. And very importantly, it published catalogs of photometrically, spectroscopically, and astrometrically variable binaries, and led to an order of magnitude increase in the number of well-characterized binary orbits in our galaxy. And for example, it published a catalog of astrometric binaries. Well, basically, and it's called like this non-single star catalog in Gaia DR3. And essentially, when you look at astrometry, you think of what is a single star motion is a combination of the parallactic motion that we see from Earth and the proper motion of the stars that moves along the sky. But there can be a deviation from that motion that you see, and that deviation can be fit by a series of models. And if you can fit it with an additional motion induced by a binary companion, then it would end up essentially entering this non-single star catalog. And so this allowed us to look at the objects that had very large astrometric mass functions in this non-single star catalog. And it's through that that we discovered Gaia black holes. And so I've taken these, so far we've discovered 3 black holes using this method of looking at astrometric orbital solutions. And 2 of them were found in DR3. Actually, one of them, Gaia Black Hole 3, was found in DR4 pre-release astrometry by the Gaia collaboration. And I plotted them on this parameter space, a diagram of distance from Earth against orbital period. And you can see this plot is currently dominated by these low mass X-ray binaries that I was referring to before. They're plotted in red, and they're all at short orbital periods. And the Gaia black holes occupy a new region of parameter space at much longer orbital periods and are closer to Earth than all of the black holes that we know of before. So these are pretty record-setting objects. Gaia Black Hole 1 is the closest black hole that we know of to date. Gaia Black Hole 3 is the most massive stellar mass black hole known in our galaxy at 33 solar masses. And as an observer, you would expect that there should be if there were black holes being discovered by the Gaia mission, that they should be in this part of the parameter space on the diagram, because astrometric searches have an inverse bias to spectroscopic searches because you're looking at the motion on the sky. The wider the orbital period, the larger the signal as the star moves around the black hole. And the closer the binary is to us, again, the larger the signal of the star moving around the black hole. But if you're a theorist, finding black holes here is very surprising. And I'll go over why that is now. So the picture we have to think about now, let's just take a binary that's isolated. It's evolving in isolation, and see whether we can produce a system like the one we are seeing. So all of the Gaia black holes that we discovered to date have low mass stellar companions around the mass of the sun or less. Whereas the progenitor of the black hole was some massive star, at least 20 solar masses, 30 solar masses, something like that. So there's a very extreme mass ratio here. So in the beginning, you have the massive star, that's the progenitor of the black hole, is on the zero-age main sequence. And it has a low mass stellar companion that hasn't even made it onto the ZAMs yet. It's a protostar. It has contracted most of the way to the main sequence, but it hasn't quite made it there yet. And by the time that low mass star is coming to the main sequence, the zero-age main sequence massive star has already exhausted its lifetime and evolved into a red supergiant, and started to initiate mass transfer onto its companion via Roche-Loeb overflow. And we know this because the predicted maximum radius of a supergiant is still greater than these AU scale orbital separations that we're observing for these Gaia black holes, that suggest there was some kind of binary interaction. And so at these extreme mass ratios, this mass transfer is predicted to quickly become unstable. And so this leads to something known as common envelope evolution, where the low mass star starts spiraling inward towards the core of the red supergiant through its envelope. And what an issue is here already that has been recognized is that the energy budget available to the low mass star, its gravitational potential energy budget, is not predicted to be enough to unbind the envelope of the red supergiant. And so we basically predicted that most of these systems should merge. But there are ways to avoid a merger event. For example, getting some other kind of energy budget from recombination energy, for instance. And so supposing that the system survives, what you end up with is a strip helium star being orbited by this low mass main sequence companion. But the story doesn't end there. Then the helium star needs to turn into a black hole. Again, the process by which this happens is uncertain. It is unclear whether a supernova occurs or whether there's a direct collapse into a black hole. It is unclear whether there's any kind of natal kick involved when the helium star turns into a black hole. So any kind of mass loss from a supernova or a natal kick can unbind the system altogether. And so the binary needs to survive this hurdle as well. So if you end up going through all of this, what you create is a progenitor of a low mass X-ray binary. Because eventually what will happen is you have this tight orbit, the low mass star will evolve, fill its own Roche-Loeb, and begin mass transfer onto the black hole. But this is much less than 1 AU. And so you cannot create Gaia black holes this way. So you're basically stuck between a rock and a hard place. The separation of the binary suggests there was binary interaction, but if there is binary interaction, you tighten the orbit dramatically. And so you cannot reach this kind of orbital separation through traditional isolated binary evolution. So this has led to theorists suggesting a smorgasbord of,
So what characteristic features hint at or indicate that there have been binary interactions in the past?
Simply because a red supergiant can't fit in the observed orbit. And so if there's nothing else that you invoke outside of the isolated binary, then you suspect that there was some kind of interaction.
Like the red supergiant would have been so much that's already covering?
Yeah, so the maximum predicted radius of a red supergiant is greater than 1 AU, right? It's like more than 10 AU. So you have this,
100,
yeah. So this low mass star, regardless of where you are, is just going to be inside the red supergiants. There has to have been interaction.
Even at these like 32 months-ish orbital timescales, which
even if you're a few years orbital timescale. Yeah.
Like basically those tensors, they still correspond to like one solar radius orbit, right? Like what's the distance, the separation of the Gaia system?
So Gaia Black Hole 1 is around an AU scale separation, and the others are few AU. So for Gaia Black Hole,
I thought I had the same. I thought that actually the Gaia paper, like some of them claimed like there might not be interaction.
for Gaia Black Hole 3 is an 11-year orbit, so it's just at that things where you can, in some models, avoid the interaction. But even then, it's thought that there are some models. It depends on the assumption you make about the maximum supergiant radius there. But definitely for Black Hole 1 and Black Hole 2, it's less than what you would expect the progenitor radius to achieve.
Why did the slide not explain their formation?
So the idea is if you do get interaction, then the mass ratio is very extreme. So the mass transfer is unstable. And so when you have unstable mass transfer, the orbital separation of a binary decreases dramatically, and you might even get the components merging. So the idea is you just go way past the scale that you observe and you tighten the orbit dramatically. So this is the traditional pathway through which these close accreting systems, the low mass extra binaries that people have thought if they formed, they had to have formed this way. But this is not sufficient. Yeah, it's not sufficient to get you to the wide scale that you see today. You just go past it. That's the main issue. And this is why immediately when Gaia Black Hole was discovered by my advisor, people were like, okay, something is wrong and we need new theory. And so what have been suggested, so this is already alluded to right now, is maybe you can modify this picture in some way dramatically enough that the stellar physics of the progenitor changes and your star just doesn't expand to red supergiant dimensions and you avoid interaction completely. Because if you avoid interaction completely, there's no problem. The low mass star can just chill at that orbital separation and the star turns into a black hole. So how can you accomplish this? One idea is that you have a very low metallicity compared to solar metallicity. Low metallicity stars tend to stay more compact in their post-main sequence evolution. There's some motivation for this because Gaia Black Hole 3, the companion is this very low metallicity halo star. So it suggests this could be the case. But the other two, Gaia Black Hole 1 and Black Hole 2, they're companions. In Gaia Black Hole 2, the companion is a red giant. In Gaia Black Hole 1, it's a very boring G-type solar type star with no anomalous abundance pattern at all. And so that's probably a different story. The other idea is that, for instance, you could have very strong winds that prevent you from reaching this radius. And another idea has been proposed is that the progenitor is actually a merger product, and there's something called chemically homogeneous evolution that causes you to remain more compact in your evolution. So there's ways you can achieve this, but you have to modify your physics somehow.
It probably only work at like lower meters. You kind of know that this one's.
So yeah, so low metallicity is definitely an idea, and that's motivated by Gaia Black Hole 3. But for instance, Gaia Black Hole 1, we know it's a solar metallicity boring star companion. So the way you understand Gaia Black Hole 1, which is like the first system that was discovered, is you have the sun and the Earth, right? You swap the Earth for the sun, and you swap the sun for a black hole. That's 10 solar masses. So that is that system, basically. So the next idea was let's just increase the number of stars until we form this kind of system. So I would say Kyle's probably would be a fan of this approach, which is dynamically assembling the system in some kind of star cluster. So for Black Hole 1 and Black Hole 2, that would be an open star cluster. Black Hole 3, that would be a globular star cluster. And one of the motivation for this is that Gaia Black Hole 3 is actually associated with a disrupted stellar stream in the Milky Way. And so it probably has some kind of cluster origin. And I put a storybook here because this doesn't get you out of complexity. You have a lot of protagonists usually in this picture, a lot of stellar exchanges, interactions going on in order to get your final system, because usually these types of systems are not primordially formed. You have to assemble them somehow. But simulations have shown you can efficiently produce Gaia black hole systems this way. So I think this is probably the leading hypothesis now for how Gaia black hole. What is important to note right now, though, is that Gaia Black Hole 1 and Black Hole 2 are not currently associated with any cluster. So even if they formed in an open cluster, that cluster must have dissolved at some point. And then finally, for fans of triple evolution, these could also, several ideas proposed for how these could have formed in hierarchical triples. I will discuss in a little more details later, but you could have a black hole star configuration or a more traditional black hole star configuration. And if you have two black holes, then the two massive stars essentially run into each other and the outer star just chills. Whereas if you had this outer stellar tertiary, you get what are called Kozai-Lidov oscillations. And this can influence the orbital separation of the inner binaries. So how do we know which one of these channels is right? We don't yet. We don't know whether each of them is right or what their relative contributions are. But what we need are population synthesis models where you assume one of these formation channels and try and predict what the galactic population of these types of systems is. And then you check whether it matches observations. Without that, you can't really know. So what have people done in this field? Well, prior to the third release of Gaia, there was a bunch of population synthesis models for the types of black holes that Gaia would find. People didn't know what Gaia black holes were before DR3, but they just generally tried to predict how many black holes would the mission find. And they all broadly assumed the standard isolated binary evolution picture. I'm going to call it IBE from now on, but I don't want to keep saying the same three words. But it's all like the vanilla type stuff, because what else would you assume? And you can see starting on, people were really optimistic, 10 to the 5 black holes. And then you get more and more pessimistic over time. And even then, you only find 2 in DR3, which is far fewer than expected. And the ones we found were a lot different than the types of black holes that people were predicting we would find. Remember, these came as a surprise. So what went wrong? Well, one thing we could point to is that a lot of these works use simplified detectability metrics, right? When you have to try and understand the Gaia selection function, they just said, okay, we'll make some kind of simplified cuts and say all these systems get detected. But the reality is a little more complex. So we need a realistic model of Gaia selection functions so we can generate mock catalogs of these astrometric binaries. So what I'm showing here is some kind of black hole binary that we've taken and placed at different distances. And the black points are actually simulated observations that Gaia makes, and the blue orbits are the fitted orbits for these systems. And this is basically showing you how a real, or a simulated system would get an orbital solution according to the Gaia mission. And this plot was produced using this code called Gaia mock. It's a public code written by my advisor, which is designed to do exactly this, basically model the selection function of Gaia, model the astrometric cascade, or all of these models that Gaia fits to determine what kind of solution is assigned to a given source on the sky. And so you can single star solutions, you can have astrometric binary solutions, you can even have what are called acceleration solutions, where the orbital period is so long that you can't fit a full orbit, but you see some deviation from single star motion. And I really want to push the point here, that cascade is complicated. Here is the full flowchart that Gaia more or less goes through in order to determine what kind of solution a source receives. This kind of flowchart is essentially reproduced by this code, but it cannot be summarized with any single cut, nonlinear or not. And so this is the main improvement.
What are those double points?
Double points?
Yeah, or they're connected with a line and it's 2 points. I'm assuming you're always seeing one.
Yeah, each of them is an individual observation, though if you're covering the orbit, which more than one time, you're going to revisit that epoch or that phase in the orbit, I assume. I don't see
everything that's on one line is multiple observations, or sorry, there's a line with dots through it. Is that what this? I just don't know what that means.
I'm not sure I'm seeing what you're seeing.
You see on the right bit. Maybe maybe I'm not describing that. You see the left panel is just dots, and then the middle one is dots with a line, and then the right one is a line with multiple dots. So is it there's multiple solutions?
So all these points are individual observations, and the lines are error bars. And the orientation of the error bars is based on the scan angle of Gaia when it comes to
that. So here you've done multiple orbits.
Yes.
I see it.
Yes, farther away.
I see.
Yeah. So I've kind of chunked up my talk so let me focus on this dynamical channel now. So basically, maybe I should move this here. Okay, so what I did, so with this improvement last year, I tried to implement this to essentially take 2 different simulated galactic populations of black hole binaries from population synthesis modeling where you assume two different formation channels. So one is Chawla et al. 2022. They assumed IBE. You might have seen that in that plot over time I showed you before. Another one that was produced after DR3, when it became, the challenges with IB became more apparent, and so they assumed dynamical assembly. That was DiCarlo et al. In 2024 from Carl Rodriguez group. And I fed them through this mock Gaia pipeline in order to produce a simulated catalog of Gaia black holes. And I want to compare their theoretical predictions to each other. And I want to see which one basically wins in terms of being closer to what we see in DR3, and also to use the observations to check whether their assumptions. Well, it's important to note when it comes to population synthesis modeling that there's a lot of knobs you can tune. And this is the driving source of uncertainty when we do this kind of forward modeling, is the kinds of systematic errors that are produced when you make an assumption. And so, for example, you have to think, what is your initial mass function, the stars you're drawing? What about the mass ratio distribution of your primordial binaries? If you start with a minimum mass ratio of, say, 0.1, and your black hole progenitor is a 20 solar mass star, then the lowest mass that your companion could have primordially is 2 solar masses, which is already larger than the companion in Gaia black hole 1. So you just kind of rule out forming these binaries primordially. So that assumption becomes important. What is your period distribution that you start off with? Is it log uniform? Is it not log uniform? That kind of matters, as we will see. And one very important assumption that people make is, how do you model common envelope evolution? So traditionally speaking, this has been done through a kind of alpha lambda prescription, which is basically just a conservation of energy argument. But as we will see, you would think the maximum, this kind of alpha parameter is what we call the efficiency parameter in this prescription. And it kind of controls how much of your gravitational potential energy budget goes into unbinding the envelope. And you would think the maximum is alpha equals 1, but because of the challenges I talked about, you can't actually get Gaia black holes usually with alpha equals 1. And so some people have basically proposed that there is some other source of energy that effectively makes your alpha greater than 1. And so in one of these models, they actually assumed alpha equals 5. So that this can also affect what your final period distribution looks like, as we will see. So I don't want to get too much into the weeds of these assumptions, because you can go to the original papers for those, but I did want to compare them and essentially say, when we think about the uncertainties in our results, this is what we should be keeping in mind. This is what we should be discussing, whether these can be improved. So what I did was essentially doing the mock observations. And so they give me some population of black holes in the galaxy. So these are all these blue points that we're basically looking top down onto the galaxy. And the yellow star is essentially where you assume the sun is, but I want to quantify a statistical error as well. And so what I do is I do bootstrapping. I essentially take the sun and I'm like, let me put it in like 100 different locations all around the galaxy and recompute like all the distances and apparent magnitudes to all of these binaries. And every single time I will run it through the mock pipeline that we have to model the selection function. I identify the systems that receive orbital solutions. So these are the Gaia black hole-like systems that I'm going to call detected from this point on. So this gives me a bunch of different bootstrap data sets that I can then combine to quantify at least the statistical error in the results. And so let's just look at the results from DR3. And here we can see we observed 2 systems. And as you might have expected from my earlier discussion, IBE basically fails to predict any kind of Gaia black hole. So this is kind of the improved estimate from what was originally there in the paper. Meanwhile, the dynamical model, which essentially was designed as an alternative to actually produce Gaia black holes, ended up being over-optimistic and overestimating the number of detections by a factor of 8. Though, however, you can see the statistical error bar that I provided on the bar plot. And again, there's some impact of their initial assumptions and POP-synth modeling that could shift your estimate one way or the other. And basically, we're like, okay, that's cool. So we have to assume the dynamical models are fiducial one from now on. And how do I make a prediction for DR4 based on this? Well, you have to recalibrate to what you actually see in DR3. So before I get into that, you may be wondering, like, can we investigate a little bit further why there's such a big discrepancy between these two formation models? Like why 0 for IBE? That seems kind of extreme. Okay, so this is a parameter space I really like to look at. So this is orbital period of all these binaries versus distance. And here you can clearly see the effect of Gaia's sensitivity, basically. So there is a time baseline for this mission that basically limits the periods to which you're sensitive to. You cannot get orbital solutions for binaries with orbital periods more than a few thousand days. And furthermore, there's a minimum motion of what we call the photocenter of the binary on the sky that you can actually detect. So the minimum wobble that Gaia can detect is around 0.1 milliarc seconds. So I plotted that for typical component masses with this kind of light blue curve on these diagram. So every point in this population that lies in between that dash black line and this A naught equals 0.1 million arc seconds line is potentially detectable by Gaia. When we actually apply the selection effects, all the orange points are the ones that actually I predict to be detectable in the 4th data release, which is coming this December, actually. And what you can see is that you initially assumed a log uniform period distribution in both cases, effectively speaking. In the dynamical model, you have all these exchanges that happen, but it doesn't materially alter the input period distribution to the point where it stops being roughly log uniform. So you still get that roughly log uniform. Whereas the common envelope evolution is the main thing that happens in the IBE model, and that creates a bimodal period distribution. You get all of the post-common envelope binaries that went through this whole process and tied in dramatically to the point where Gaia doesn't detect them anymore. Then you still have this cloud of really wide, non-interacting binaries that are beyond Gaia's detection limit. And so diabolically, this period gap where Gaia astrometry is the most sensitive is exactly where an IB, a traditional vanilla model, would predict very few black hole systems to live. And this is why you end up getting 0 in DR3 and like just a handful in DR4. Meanwhile, the dynamical channel just gives you a lot more systems in that period range, and then that's why you end up being so optimistic. And so as you get to future data releases, the main thing that happens is you end up discovering further away systems as your time baseline increases, and systems with slightly longer orbital periods.
Yeah, but those binaries, those white binaries, they're not like being disrupted during the formation of the black hole. Like,
yeah, some.
This is only considering them like immediately after, like before the black hole forms, or what? Like, I would expect a lot of these to be. I don't know. I would expect the close binaries to be much more data points compared to the white ones for systems that survive that stuff.
Yeah, so this kind of depends on what your assumption of black hole formation is and black hole needle kicks and stuff like that.
Yeah, but I mean, there's always still like a Blau kick and like, still a lot of these should be like neutron stars, right? Like this is, or did you already select for like black holes?
So you're right that if you have like this Blau kick, that a lot would be unbound, especially for low mass stellar companions. But I'm trying to remember exactly the supernova prescription that you used. But for example, you could suggest that black holes form by a direct collapse.
Yeah, no, that I understand. But just so these data points, they're taken, these are like the periods right after the first compact. So this is a snapshot of the periods from like binaries that have like a compact object and like a star companion.
Yes.
And then do you do other selections? So do you do selections on like what the secondary star mass should, is it already incorporated in this diagram, or is this just like,
this is the model from that paper Chawla 22, and it's basically all the black hole luminous companion binaries in the Milky Way. So it's for both main sequence and post main sequence companions. There's no other selection I have imposed. I took essentially the data file they gave me and plotted it on this diagram.
Okay. Yeah, I have to think.
Yeah.
For the dynamical systems, why is there the hard cutoff?
Yeah, good question. I was just about to point that out. So you see all these streaks, and this is because sometimes to save all of that computation time, they take the binaries that they're simulated and basically duplicate them in the galaxy. So that's why you see these horizontal streaks. And the cutoff, which seems to align with the dashed line, is, so I've basically given an approximate period detection limit for DR4, that that's not the reason why they align. This artificial cutoff is because their initial assumption for the semi-major axis comes from this paper Sana 2012, which is basically an observational paper so like these empirical distributions for massive star binaries, basically. And it's because humans don't live forever, basically. And so there's a cutoff in terms of what they were able to observationally constrain. And that cutoff is basically around there. The good thing is for our case, because that is around the detection limit of Gaia and DR4, that doesn't affect what we say is actually going to get detected by Gaia. You can see the orange points don't quite push up against that limit yet. Now, we caution that once you get to DR5, which is the final data release of Gaia after its entire mission observing time, that it probably runs up against this limit, and then you can't have that kind of artificial. But yeah, it's a good question. It's a nuance. We were basically working with what we had at the time. There have been some more population census modeling that's been done since then, where people are trying a little more to understand what the effect of the knobs are. Though I'm not, I think there's like a work in progress for the dynamical model in terms of training the nodes, but it's not even out yet. So,
and for these dynamical formation, do most of them go through common? Like, are the bottom ones?
I think the idea is the ones that go through common envelope are just not the ones. These are, so almost everything is not primordial. Basically, nothing is primordial. These are all like exchanged binary. So the ones that are forming is you have like this whole flow chart of, this star comes in and swaps out, and then this star comes in and swaps out, right?
Yeah, so you basically expected like, at least for the dynamical one, the values of like, say what they assume for alpha are not going to impact the outcome there. It's just going to impact the left. Right?
Yeah, the value of alpha is not as critical for the, yeah.
Because this one, I think it's just like if you change alpha, this is going to shift.
Yes, this is true. Yeah.
Sorry. Sorry, also, this is like how our talks there often happen.
Yeah, I actually, yeah.
Okay. Very interesting.
About the colors of this plot.
Yeah.
I mean, what are the gray points? The outside detectability limits, or is that just like a very light blue?
That is a very low alpha blue.
Okay. And where are those points congregated?
So basically, understand might be hard to see. So this stuff is all low alpha actually, and this is also low alpha, and these points are a little bit higher alpha. Yeah, it's hard to distinguish because there's so many more points here and there than there.
And about the contour line with the varying semi-major axis, or not semi-major axis, but detectability criterion in terms of Gaia separation in sky, arc-second separation. Like, what is the difference between like a 0.1 milliarc second, which is like the complete limit for a Gaia survey, versus like a 1.0? Like, what does that communicate?
So this contour is to guide the eye, basically, and this is the most critical one because it's the detection limit for Gaia. So everything between these two is kind of, so if you don't want to use the opacity of the points in order to distinguish what I'm calling detectable and potentially detectable or not detectable, I just want you to look at between these two lines, basically. And what I'm trying to communicate here, so what is A naught? A naught is particularly, so A is semi-major axis, A naught is semi-major axis of the photocenter. There's like some distinguish thing there. For a luminous star and a dark companion, they are the same. Well, actually, yeah, for the luminous star and the dark companion, they're the same because you're only getting light from one star. If you had an equal light ratio binary, the photocenter would never move, right? So there's some nuance there. But the idea is basically, as you get some binary motion, right, the photocenter of the two stars will wobble and move around. So this is what astrometry is trying to detect, right? And so the magnitude of that wobble is measured in milliarc seconds for Gaia. That's how precise it is, essentially. And so 0.1 milliarc seconds is roughly, if you look at its orbital solution catalog, the minimum motion that is able to detect and say, hey, there's a binary here, right? As you get wider and wider wobbles, right, that curve moves on this diagram, and that's where such a binary would live, basically at longer orbital periods or, higher black hole masses, et cetera.
Gaia guarantee 0.1 for all the stars with that whatever photometric threshold value that they set, or is it like a fraction of all stars which gets to 0.1? Because every time the survey is always...
There are quality cuts based on uncertainties and things like parallax and semi-major axis. And these quality cuts are nonlinear, and they're described in a paper, Hallblocks 2023. And so we have that, we model those, we put those cuts in when we're doing the mock pipeline. But I don't know whether I can straightforwardly give you an answer if this percentage gets in or not. But so the one good thing about the fourth data release that is coming December, why are we so excited, is because they are promising to publish all epoch measurements. They didn't do this in DR3, so you just have to basically take whatever solution they give you and vet it yourself. In DR4, you can just fit everything yourself. You don't have to care about what quality cuts they do, right? You can just use your own quality cuts. And so, like, actually going on that point, how do we forecast how many we will discover in DR4? And that's what I'm showing here. And so here, what I've done is make simplified cuts on the parallax and semi-major axis I was just talking about, and saying, like, if we assume these are the cuts for something entering, like the orbital solutions that get accepted, basically, then how many Gaia black holes do we find? So you take what the dynamical model gives you and recalibrate to DR3 roughly. So this is all I'm doing. And to order of magnitude, you think around 30 Gaia black holes are detectable in DR4 is my prediction. And there's around 10 to the 4 total of these AU scale systems in the galaxy. This is what I can predict from forward modeling. And so the upshot is that basically we have around 2 to 3 Gaia black holes right now. And this will increase by an order of magnitude in DR4. So this is what we are excited for. You actually have to go out and vet them and confirm them and so on and so forth. But once you get an order of magnitude increase in a sample, you can start doing more statistical fun stuff with them. And so this was like the first paper that made a realistic prediction, I would say, using the full modeling of the Gaia selection function for what we will find in the next data release coming this December that we are. So you can ask what the characters of Gaia black holes are. Maybe I'm obligated to show some imposing looking corner plot in this talk. And then, of course, nobody looks very closely at any single panel. So I'm just going to summarize this corner plot and say, what we can do with this forward modeling is say, okay, we have the distribution of parameters for all the black holes from the populations in this modeling. You apply the selection cut, it gives you these different distributions. And what happens is you get a bias toward closer systems, brighter companions, more massive companions. Like this is something exactly you would expect. And then I've plotted where black hole 1, black hole 2, black hole 3 lie in this corner plot. And the summary there is basically black hole and black hole 2 with these 10 solar mass-ish black holes, 1 solar mass-ish companions, are very typical of what you expect to find, basically. So it's not surprising that we've found those systems. Black hole 1 being the closest of the ones we know today is okay because you're going to find the closest ones first in the data that you have. Black hole 3 stands out as a kind of a little bit of an outlier. And there's a reason for this. Basically, the Gaia collaboration got antsy. And they were like, oh, like we want to publish this one system early because it's like this huge signal that is screaming at us. And we're not supposed to do any science, but it's okay in this one case. And so they published it a little early so people could think about that one system. And so it makes sense that it is an outlier in terms of black holes. So I want to return to this one, I can modify the physics of isolated binary evolution idea. We already talked about common envelope evolution, and if you want to just not make any modifications, you at least need to have an efficiency greater than 1, which is a little unphysical to form these types of systems. And so people have been thinking about alternatives just like this year about other modifications you can make to binary evolution physics to form Gaia black holes. And this kind of little radical idea is that maybe you can have these extreme mass ratios and yet still have mass transfer that is stable rather than unstable. So it could be more stable than previously thought. And the way you do it is by having mass transfer being a lot more non-conservative than previously thought. So conservative mass transfer means mass is retained, non-conservative means mass is not retained. And if you want to get into the details of the physics, or if anybody here knows about like angular momentum loss prescriptions and binary mass transfer. So anyways, yeah. Angular momentum is normally you think about it being lost via isotropic re-emission from the vicinity of the accretor. But the modification here is that it's being lost via wind from the vicinity of the donor. And so in layman's terms, or at least for the way I understand it, so we can see down here how the geometry of the mass transfer looks like for different mass ratios. So you have like an equal mass ratio binary, it looks what you kind of think of like a little deformed ellipsoid. And then you see at a very extreme mass ratio, you basically are like feeding like a poor little low mass stellar companion with like this hose of material, and the cross section that you see is quite small. And so at some point, you just like when the donor star, which is very massive, starts losing mass, you just start losing it as a wind from the donor rather than feeding it to the companion. And so the companion doesn't actually accrete that much material. The mass transfer is quite non-conservative and it ends up being stable. You can even get self-accretion from the donor onto itself. There's a lot of interesting investigation of this channel going on right now for forming Gaia black holes. People have done population synthesis modeling. They've done MESA simulations of this and shown that you can produce these types of systems with this modified assumption. And so this is just one exciting direction I want to highlight.
Because sometimes Alexandra, like for these kind of models, she has kind of two extreme models. But like usually what she does is like she uses this like velocity new updated like stability criteria from the like paper in 2017. But then there's one that basically says like, okay, we're gonna allow all mass ratio, basically change the critical mass ratio to like a factor 8. But then that model, basically everything only forms stable, like you almost never have a common envelope. So, that's one way. And then what she does though is that she says like, oh, but actually when you use that model, it kind of results in some like physical results where like, oh, even if the star is like 10 times bigger than its like Rorschach radius, it still can proceed stably, which is kind of crazy. Like those should merge. And so she has this like switch models, right? She says like, okay, we're gonna add this safety switch that like stops those systems from appearing in our population synthesis. Do you know, is she using like these kind of models there, or is this something different?
So I'm not sure too much about that level of detail. I couldn't tell you, but I would say just look at these papers.
Okay.
Yeah, and I wouldn't say like this is like, wow, we've solved the problem. Of course, there's like a huge amount of uncertainty still left. I just think that thinking radically in this way might be one of the ways to save isolated binary evolutions.
Save it. I don't think this would be the way to save it, but that's my opinion.
Yeah, they use MESA here.
They do?
Yeah.
Yeah, and the point is that if your mass loss mode is from the donor, the shrinking is less dramatic than if you first transfer the mass. This is kind of the issue with the traditional like A dots. And so in this formalism, it's almost like the wind. It's almost like the genes mode, almost.
Mm-hmm.
And so these things don't become catastrophically close together.
Okay, it's based on MESA. It's not.
Yeah, this is MESA proof of concept with MESA, and then this is 7.
Yeah,
the POPSIT.
it also uses MESA. For a second.
Yeah, they're not binary. So this was with a binary.
No, the McBelly one is also binary.
Yeah.
Really?
Yeah, it's like her new paper.
Oh,
Yeah.
nice.
If you're interested in POPSIT model, check it out.
Yeah.
Okay. I don't know, how much time do I have left? 10 minutes?
Like 5.
5 minutes? I will try and go through this quickly, and if people are like super interested in triple evolution, you can stop and ask questions. I just want to mention, because so I have a collaborator in my group, Cheyenne Shariat, who really likes triples. So again, recapping how this works, there are different populations. Usually, this was first proposed for black hole low mass X-ray binaries, and we'll see why. And the idea is, these things called Kozar-Lito oscillations, where essentially you have this exchange between eccentricity and mutual inclination between the tertiary orbit and the inner binary. And so you can make the inner binary very eccentric, even if it started off circular. Then it gets very close at periastron, and then tidal effects start taking over. And then what you can end up doing is shrinking the orbital separation of the inner binary. So this is the general idea for how you can form low mass X-ray binaries by not having interaction initially, let the black hole form first, and then bring the components closer together. For Gaia black holes and neutron stars, this is a more recent thing. People have found triples can also help you there. The idea is delay common envelope evolution, have the components become wider initially, and if you have them become wider initially and then have common envelope start, then maybe you can get a wider final separation. And again, this is kind of a rare outcome, but you can get it to at least work because triples can help you. Is there any kind of observational evidence for this? Well, one thing that was really cool is in 2024, Kevin Burge and my advisor were just essentially looking at Aladdin, and they noticed for this very well-studied LMXB V404 Cygni, there's this source that's around 1.4 arc seconds away to the north. You can actually see it right here in this this image right here. And so this star down here is V404 Cygni. It's the LMXB. And for many decades, people were like, oh man, this is an annoying chance alignment. I have to change the alignment of my slit when I'm observing and blah, blah, blah. But then if you just look in Aladdin at the Gaia information for these two stars, you will find that the proper motions are very similar and they're consistent. And they got some radial velocity follow-up and then found that these two stars it's not just that they're coincident, like they are actually gravitationally bound together. So this star is a tertiary to the system. And it's very weakly gravitationally bound. So this is one of the systems with the strongest evidence that at least some black holes do not receive natal kicks and form via direct collapse. Because if there was any kind of real supernova here, then that star would not be gravitationally bound anymore. So it's a very interesting system. And this kind of motivates that because V404 Cygni is nearer and brighter than other black hole LMXBs, that there might be tertiaries hiding around other systems that are harder to detect. And so I have a very recent paper where I've actually gone out and looked mainly at both black hole low mass X-ray binaries and Gaia neutron stars. I understand I haven't introduced Gaia neutron stars. Basically take the black hole and replace it with a neutron star. So there's population of wide neutron star binaries that have also been discovered with this exact same method. And I basically looked for stars that we have not detected before or not resolved before. You can see stars that are hiding in the halo, stars that you thought were a single blob getting resolved. And the trick here is to use adaptive optics and near infrared imaging to do that. So I've been doing a lot of that. And the idea is you can use chance alignment probabilities and make arguments about what is promising as a candidate and what is not. With one epoch, you can't establish physical association, but you can start probing what could be a tertiary or not. I also actually used high contrast imaging techniques to try and get to the speckle dominated regime and even look for candidates there. I didn't really find anything. There is one candidate. You can use DR3 to kind of rule out some other candidates. It's right over here. This probably requires, it's an M dwarf. You wouldn't expect it to be there just by chance. I don't actually think it's a tertiary, but it's exactly where you would expect a tertiary to be. I can talk more about this if people are interested. Cheyenne has a paper coming out where he looks at stuff like this. So this is what, if you do try and subtract the PSF, this is kind of what it looks like using a library of reference stars. There's residuals. It's not perfect with a small library, but you can actually try and get to closer separations. The point is, if you don't detect anything, you can still put constraints on what types of tertiaries there would have existed because we would have detected them. And if anybody is interested in exoplanets, this is called a contrast curve. So it tells you what you would detect as a function of separation. You can essentially convert this to limits on the mass of main sequence tertiaries and the temperature of white dwarf tertiaries. What I find in summary is that at around 500 AU for the Gaia black holes and neutron stars and 2000 AU for the most distant black hole XPs, I can essentially rule out any plausible main sequence tertiary. So this is the main result of that paper. The problem is I cannot rule out white dwarfs, and white dwarfs are probably the most common types of tertiaries that there are, and so you need JWST to get to that. So good luck convincing the JWST proposal committee. But essentially, this is trying to place limits on channels to predict main sequence tertiaries that actually remain bound today. So this is kind of like one of the first observational tests of this type of hypothesis. So I also mentioned an inner black hole binary scenario. I've looked at this in the past. It's the only observational test of this kind of hypothesis where it's a black hole star. The point there is that if you have an inner black hole binary, even though it's not merging, it will induce a non-Keplerian perturbation to the orbit of the outer star, which you need meters per second precise radial velocities to find. So I borrowed my exoplanet friends' espresso instrument that they use and looked at Gaia black hole 1. Here's how precise the espresso radial velocities are compared to normal radial velocities that we use in stellar observations. It's now one of the most well-constrained binaries in the Milky Way, I would say. And from that, we were able to constrain this and not find evidence for inner black hole binary. And because people here work on LIGO, I think, or gravitational waves, I would like to say that the constraint that we put is such that if there was a black hole binary in Gaia black hole 1 in the interior that we were not finding, and it was at a smaller separation than 1.5 days, it would emerge in a Hubble time. So there's a fine-tuning problem there. So again, if people are interested in this, I can talk about that. Gaia Black Hole 1 is the most well-studied object in our sample. You can combine all the constraints I've talked about here in this nice colorful diagram from AO imaging, from our radial velocity follow-up, and rule out a huge part of parameter space for it being in a triple rather than binary. So this is also, it looks like triples are not a promising pathway for Gaia black holes and neutron stars. So that's why dynamics is winning right now. But there's still white space on this diagram. So my collaborators that are fans of triples treat this as a way to write more proposals. And, you know, I guess if you want to keep reducing the white space, you need to go to interferometry, which I haven't done yet. That's my spiel as an observer. I'll throw up my summary slide here. A few minutes left. Thanks. Yeah.